in order to determine the value of m1, that is bending moment at any section, any point due to unit force applied at coordinate 1, then m2 is determined from applying unit force at coordinate 2. Okay. So, first we are going to determine m1 value. So, first consider the AB portion. So, let us consider section xx, which is x distance from the end A. So, both the cases it should be same for m1 and m2. So, both the case we have to determine the moment for A, B, BC and CD portion, then both origins are same. Okay. So, that is why it seems correct. Okay. So, first for AB portion we consider section xx, which is x distance from A. So, therefore, the limit for the AB portion is 0 to 4. If x is equal to 0 means it at A x is equal to 0, at B x is equal to 4 meter. So, now bending moment m1 is equal to, so it creates Hawking moment minus 1. Okay. So, that thing is for portion AB, origin A, limit 0 to 4, then m1 is equal to minus 1. Then for CD portion, I had considered section xx, which is x distance from the end D. Okay. So, therefore, what is the limit? Limit it varies between 0 to 2. So, bending moment at the section xx is on the right of section xx is equal to 0. There is no force on the right side of that section. So, therefore, the bending moment is 0. So, for CD or DC portion, origin is D, limit is 0 to bending moment m1 is equal to 0. Then for BC portion, BC or CB portion. So, for this also I have to consider section xx, which is x distance from D. So, therefore, limit varies between 2 to 6. At C x is equal to, at B x is equal to 6. So, this is 6 meter, this is 2 meter. So, therefore, the limit for CB portion is 2 to 6 meter. Then bending moment at section xx on the right side of section xx is equal to, so only VC into x minus 2. Okay, this distance is x, this is 2 meter, x minus 2. So, therefore, CB D as origin, limit 0 to 6, VC in bending moment is equal to VC into x minus 2, where VC is equal to minus 1 by 4. Then for M2 moment, so we have to apply unit force at the coordinate 2. Okay. So, at the coordinate 2 is this is the coordinate 2. Okay. So, we applied unit force, then moment for AB portion. Okay. So, again we have to consider section xx, which is x distance from A. So, limits are 0 to 4 meter. So, bending moment is equal to 1 into x. So, it is a sagging moment, therefore positive. So, 1 into x moment. Then for CD portion or DC portion, so again take a section xx, which is x distance from D. So, limit 0 to 2, bending moment on the right of the section is 0. There is no force on the right of the section. So, therefore, bending moment is 0. The next for CB portion. So, again take a section xx, which is x distance from D, limit 2 to 6, the bending moment is equal to VC into x minus 2, where VC is equal to 1. So, therefore, 1 into x minus 2. Then flexural rigidity of each portion. For AB portion, 2 times, other 2 portion have single times flexural rigidity. Then determine the coefficient of flexibility matrix, that is the element of flexibility matrix. F11 is equal to integration of m1 dx divided by ei. So, in the F11 both I and j are 1. So, that is why this equation becomes like this, integration. So, we know our general equation Fij is equal to integration of mi mj into dx divided by ei, where I and j are 1. So, therefore, integration m1 into m1 dx divided by ei. So, we should integrate for entire portion of the beam. Okay. So, no part is neglected. Okay. So, first for AB portion, then DC, then CB. For AB portion, limit varies between 0 to 4, m1 is equal to -1, and Young's flexure rigidity is equal to 2 times EI. Then for DC portion, so limit varies between 0 to 2, m1 is equal to 0, flexure rigidity is equal to EI. For CB portion, limit varies between 2 to 6, m1 is equal to minus x minus 2 by 4. Then flexure rigidity is equal to EI. Finally, integrate this thing, f11 is equal to 10 by 3 EI. Then f12 or f21 both are same. So, which is equal to integration of m1 into m2 dx divided by EI. So, for AB portion, again limit 0 to 4, m1 is equal to -1, m2 is equal to x, then EI is equal to 2 times EI. Then CB portion, limit 0 to 2, m1 0, m2 also 0, dx divided by EI. Then for CB portion, limit varies between 2 to 6, where m1 is equal to minus x2 by 4, m2 is equal to x2 x minus 2. Then flexure rigidity is equal to EA. Then after integrating, f12 f21 is equal to minus 28 by 3a. Then f22 is equal to integration of m2 into m2 dx divided by EA. So, again substitute m2 values for the all the portion. Then finally, f22 is equal to 32 by EA. The flexibility matrix is equal to f11, f12, f21, f22 is equal to 10 by 3a minus 28 by 3a minus 28 by 3a 32 by EA. Then third step, now remove the redundants. Now remove all the redundants and find the deflections in the direction of assigned coordinates due to given loading. Okay. So, we are going to determine the deflections. So, it may be a translation or rotation in the direction of assigned coordinate. So, what is the first assigned coordinate? First assigned coordinate is the moment coordinate. So, we are going to determine the rotation at the coordinate. Then second assigned coordinate is the force coordinate, that is the vertical force. Now, we are going to determine vertical deflection. Okay. So, in this third step, first we remove the redundant, then determine the rotation at the end A, then vertical deflection at end A. Okay. So, after removing the redundant, it becomes a primary structures. So, it is a determinate structures. It's like a double overhanging. So, now determine the support reactions. For this, we have to apply equilibrium equations. Summation of mb is equal to 0. So, while applying this equilibrium equation, we determine the Vc value. So, Vc is equal to minus 50 kilonewton. Then summation of V equal to 0. So, from that equilibrium equation, Vb is equal to 230 kilonewton. Okay. So, now we are going to determine the slope and deflection at the end A by using unit load approach. Okay. So, in order to for slope is equal to integration of capital M into small m into dx divided by EI. So, capital M means the bending moment due to external loads, small m1 is bending moment due to unit moment applied in the direction of record slope. So, in the unit load approach, if you want to determine the slope means, so we should apply unit moment in the direction of record slope. Then deflection is equal to integration m capital M small m to dx divided by A, where m2 is equal to bending moment due to unit force applied in the direction of record deflection. So, if you want deflection means, we should apply unit force in the direction of deflection required. Okay. So, we already determined the value of m1 and m2 in the previous table. Now, we are going to determine only capital M value, bending moment due to external load. Okay. So, again you should make a table like this, or you may add this capital M portion in the previous table itself. Okay. So, again portion, origin, limit, EI, then capital M. So, all are same. First consider AB portion, then origin is same, A, limit is 0 to 4, A is equal to 2 times A. Then moment, bending moment is equal to minus 40 into x square by 2. So, for AB portion, we have to we consider the section XX, which is x distance from A. Okay. Now, take a moment on the left of this section. Okay. So, on the left of this section, uniformly distributed load is there. So, therefore, it creates hogging moment, it is a downward force, it creates a hogging moment. So, moment is equal to minus 40 x square by 2. Then, for DC portion, origin is D, limit is 0 to 2 meter, flux velocity is equal to E A. So, we are taking moment at section XX, which is x distance from D. So, on the right of this section XX produces a moment of minus 20 x. Then for CB portion, again origin is D, limit 0 to 6, flux velocity is equal to E I. Then now bending moment is equal to minus 20 x minus 50 into x minus 2. Then slope at the end A, slope at the end A is equal to integration of capital M into small m on dx divided by E I. So, substitute. So, integrate it for the entire span, for first AB, then BC, then CD portion. Substitute 0 to 4 for AB portion, limit varies between 0 to 4, capital M is equal to minus 20 x square, small m1 is equal to minus 1 dx divided by, so flux velocity is equal to 2 times A. Okay. Then for DC portion, so limit varies between 0 to 2, capital M is equal to minus 20 x, m1 is equal to 0, then flux velocity is equal to E I. Then for CB portion, limit varies between 2 to 6, capital M is equal to minus 20 x minus 50 into x minus 2, then m1 is equal to minus x minus 2 divided by 4. After integrating this equation, finally the slope is equal to 666.66 divided by E I. Then deflection in the second coordinate is equal to integration m capital M small m to dx divided by E A. Now, substitute m and m2 values for each and every portion and integrate it. Finally, the deflection is equal to minus 2453.33 divided by E A. Okay. The final step, the redundant reactions. There are two redundant reactions. It can be represented in a matrix form like this. It is a column matrix. It is a single column matrix R1 R2. 2 redundant is equal to flexibility inverse into net deflection at the coordinates 1 and 2. So, net deflection at the coordinate 1 is equal to delta minus delta 1 L, sorry, not net deflection, it is a deflection induced by the redundant force. So, use this general equation, or redundant reaction is equal to flexibility inverse redundant reaction is equal to flexibility inverse matrix into net deflection minus deflection induced by the external load at the assigned coordinates. Our first redundant is moment, bending moment. Second redundant is vertical reaction, MA VA. Then flexibility matrix we already know. Substitute this flexibility matrix. Then delta 1 net deflection at the assigned coordinates are 0. So, therefore, the delta 1, delta 2 are 0, delta 1L and delta 2L is already known. Okay. So, in the previously we determined these two values. So, delta 1 is equal to 666.66, then delta 2L is equal to minus 2453.33 by A. So, after taking inversion, then multiplying these two matrix, MA VA is equal to 80/100. So, from that MA is equal to 80 kilonewton meter, VA is equal to 100 kilonewton. So, After determining the values of this redundant, now determine other two support reaction with the help of equilibrium equation. So, apply two equilibrium equation, summation of moment equal to 0, then summation of V equal to 0. So, from that equilibrium equation, V c is equal to 30, then V b is equal to 50. So, after determining all the support reaction, now draw the shear force and bending moment diagram. Bending moment. So, bending moment, you already know about how to draw a shear force and bending moment diagram. So, bending moment at A is equal to, it is a fixed end moment minus 80, then M b is equal to 0, then M c is equal to minus 40, M d again 0. So, this is the net bending moment diagram. So, it includes both hogging and sagging. Okay. So, net bending moment diagram. Then draw the shear force diagram. At A on the left side is 0, on right is 100. At B, left side is minus 60, right side is 10. Then at C, left side is minus 10, right side is 20 kilonewton. At D, left side is 20, right side is 0. So, this represents the shear force diagram. Thank you.